so the title is Impact of Functional Safety on Software Architecture. That's a mouthful. And when I created the presentation, my first question to myself is, this is actually a question mark. Is there an impact, and we should all ask that, is there an impact of functional safety on software architecture? We know, most of us probably know there are quality attributes and techniques and tactics. And so the idea is when we're applying this idea of safety to other industries, is it the same? Is it different? Is it new? And that's what we're going to discuss today. Okay, so just a brief agenda. I'll give a very short introduction of myself and the company I work for, Visteon Corporation. And then a couple of goals for the presentation. We'll spend most of the time discussing what is functional safety. So if you get only one thing out of today, that would be a good takeaway. And then a brief connection of that topic to software architectural safety, and then we'll conclude. Okay, so I've been working in the software engineering space for approximately 25 years. And most of that time has been in the embedded systems, hard real-time systems, deterministic, and most of it in the automotive industry, a little bit in the industrial tooling. So in that time, I've seen a lot of growth, both in software functionality and in complexity, and the requirements we're trying to achieve. So architecturally, things look a lot different now than they did 25 years ago. And I will tell you, and you have noticed yourself, even in the automotive space, what you're seeing in the vehicle is greatly different than just a couple of years ago. And that all impacts us when it comes to architecture. Okay, so from a corporate standpoint, again, I work for Visteon Corporation. We're what's called a Tier 1 supplier. So we supply complete solutions, and you can see the spaces that we focus on. Cockpit electronics is the terminology. And today's vehicle, the cockpit would look similar to what you're seeing here. And we focus, or we're the leader in the digital cluster space. And again, if you had a vehicle 5 years ago, you might have seen physical gauges with stepper motors there, maybe a mechanical, what looked like a mechanical odometer. Today, it's a little more obvious what's happening behind the scenes. You're seeing a display and a lot of electronics behind it. So it's a little more obvious. There's a lot of software here now. Where it wasn't so obvious, there was a lot of software behind all those gauges and chimes and things that you might have heard in your vehicle a few short years ago. Okay, so the goals again for today. I want to introduce this concept of functional safety. And if you were at the keynote this morning, you saw reference to some standards, ISO, IEEE, UL. So we'll be talking about one particular standard and going through it that Phil mentioned in the keynote, ISO 26262. And it's not important that that relates directly to maybe the industry you're in. The point is to look at what these standards are saying from these regulatory or standards organizations and how that impacts us as software architects. And then the second goal will be trying to relate that to the things that we know about software architecture. Okay, so functional safety, what is it? Okay, that, based off the presentation we just saw, is it depends. Okay, so depending on your industry, you may have a standard on what functional safety is. I have only a few examples here, but you can see it spans many industries. I live in the automotive space, so that's the first spec, but you'll see defense, tractors and machinery, medical, nuclear, and it makes sense to us on some level that anything that can cause harm in some way or go awry should have some sort of standard. And that's what we're trying to represent here. So I would challenge you in the industry you're in to, if you're not aware of it, do a little research and see, is there a safety standard for functional safety? Now I'll describe what does functional safety actually mean. And here we're going to now dive into the ISO spec, which is applicable in the automotive industry. So if we read the definitions, it's actually a chain of definitions. I won't read them all, but I do want to go down about halfway. The first definition, absence of unreasonable risk due to hazards caused by malfunctioning behavior of electronic and electrical systems. That's a mouthful, and it has other questions in there. The first question might ask, what's unreasonable risk? Okay, unreasonable risk is risk judged to be unacceptable in a certain context according to valid societal moral concepts. And now we're getting into societal impact. So we ask ourselves again, okay, unreasonable risk is risk. So what is risk? Risk is the combination of the probability of occurrence of harm and the severity of that harm. So now what is harm? Harm is physical injury or damage to the health of persons. And that's as far as I need to read before it hits you in the face that we're not talking abstract concepts here anymore. We're talking about actual people and danger. And depending on your industry, this may be well known. If you work in defense, if you work in the aircraft industry, and this is the automotive. But I would, again, challenge you, even if you're working in consumer electronics, there is the chance to do real physical harm to people. We saw in the keynote this morning some of those dangers. It's hard to even know what the risks are. And we need to start thinking about these are real risks to real people. We're not talking about just, okay, if my process crashes, I need to restart it. Yes, that's true. But do you need a duplicate process? Is restarting it the best course of action? Maybe you delegate the work. These are the questions we need to start answering. Okay, so ISO 26262 is, again, the functional safety standard for automotive. And there's three, it's a large set of standards. It's not just a one-pager. There's hundreds of pages with hundreds of statements in there. I picked three key concepts for today. One will be, how do you categorize functional safety? Obviously, certain functions need to adhere more strict to safety standards than others in a vehicle. Second is, if I have some level of functional compliance on function A, how do I keep that from interfering with another more safety critical functionality in the vehicle? And then third, we'll talk about other areas of development that we need to look at safety from software architecture standpoint. Okay, so the first is called automotive safety integrity level, and that, if you want to think about it, is a categorization of functional safety. The idea is here that you need to take the severity, the exposure, and the controllability. And there are some in the standards, there's a way to then classify what safety level is needed for that functionality. And for severity, we're actually talking about harm. This is, ranges from there's no harm if this functionality goes awry to real life-threatening physical harm to somebody. The exposure is think of it as the probability that, in this case, the vehicle would be exposed to the event that could cause that harm that we're trying to avoid. And the controllability is, for us, we're talking about use cases here, really. So think of actors, which would be a driver in this case. What is the ability of the driver to avoid exposing the vehicle to the conditions that would cause the harm? So you roll all this up into essentially a matrix, and you get these categories from A to D. D meaning this is very critical functionality. We need to take all of the safety measures we can to avoid this from happening. And A is much less stringent. And you would ask yourself, well, why different categories? Well, an example, you may have a tachometer in your vehicle. If the tachometer is not working, the odds are you still have a functioning speedometer, you can still brake and accelerate, you can still steer, so it wouldn't cause necessarily any great harm to anyone. So that might be not as safety critical as, okay, some of the examples you saw this morning where you have some autonomous functionality and it goes awry and something bad could happen. Okay, so after the safety integrity level is determined for functionality, then we want to ensure that we have this concept called freedom from interference. And this is a way to guarantee, in theory, that one of these lesser safety critical functions does not interfere with one of the higher. So if we say something is ASIL A, we want to ensure that if that does fail, it does not adversely impact something that is safety critical. And that concept is called freedom from interference. Now at the bottom, you'll see, some safety categories. And if you look at those categories for faults, you may recognize these. Okay, from as software architects, we know about these already. There are timing considerations, memory protections, exchange of information, which is communication mechanisms. So for us, you're starting to see whatever terminology is used in these standards, it's not new information to software architects. So if we go through these fault categories, let's just briefly go through here. We're dealing with timing and execution. So what does this mean? The types of faults that could happen are things like deadlocks and live locks, or incorrect allocation of scheduling time for one safety critical functionality versus something that's not. In the protection mechanisms, if you read through them, you'll see fixed point scheduling, time trigger scheduling. Again, these are, if you're familiar with the quality attributes, we're starting to see here some tactics that we know about to adhere to scheduling that we're trying to achieve. When it gets into memory protections, the faults, again, are things that are probably not new to you, but are specified here. Corruption of the content, stack overflow and underflow, memory access allocation issues, and the protection mechanisms, again, looking at that, you're probably starting to see other tactics that you're already aware of, CRCs and ECC and redundancy and restriction of access. When it comes to exchange of information, again, we're talking about communication here. If I have a safety critical functionality and something that's either not safety critical or a little less safety critical, the idea here is to protect the very safety critical from the less. So, and the faults can be repetition of data, loss of data, delay of delivering the data, incorrect data. And the protection mechanisms, which are numerous, you can just browse through those and you'll see, again, these are tactics that are mentioned in many software architecture texts on how to avoid or prevent different data loss. Okay, so that was so far, how do you categorize faults and safety functionality? Second was, given that, how do we protect one level from another? And this is the third set of concepts from at least the automotive specific specification. This deals with all the other areas that we work in as software engineers. And how do we achieve safety through some of these other things? And you'll see some of these are process and some of these are technical. Starting at the top, there are, in the ISO spec, modeling and coding guidelines. And there are methods to achieve safety even at that level of process. So depending on your safety functionality, whether it's critical or less critical, you would apply 1 to n of these methods to achieve that. And this morning, I think you heard self-certification. This is part of that process, is that as software engineers in the automotive industry, we are expected to go through the ISO standard. We're expected to adhere and then justify that we have taken all of the steps we can to do any 1 to n of these methods to prove functional safety. So again, for modeling, you can have strong typing, defensive programming, style guides in your organization, naming conventions. That's at kind of the coding and modeling guidelines level. Notationally, for us as architects, I'm sure we have all published what we think are standards within our organization. And the key is to make sure that those standards also satisfy whatever functional safety standard applies to your industry. So for automotive, you'll see some of the methods here. Use of natural language, informal notations, semi-formal notations, and formal notations. Now, according to ISO, UML, and SysML, those are semi-formal notations. So that gives you an idea of where we're falling in. And again, depending on the safety that you're trying to achieve for a particular function, you would apply, again, 1 to n of these. It's not an either-or case. Next is principles of software architecture design. And what are we trying to do here? Consistency, simplicity, a lot of the abilities. Yeah. And the methods are, reducing size and complexity, adhering to cohesion and coupling standards, increasing, decreasing. It's a balancing act. But those need to be decisions that are made in the architectural design and then justified and documented. And then the next two are around error detection and handling. And these, again, if you look at the methods mentioned here, data range checks, plausibility checks, error detection codes, under handling, there's safe states, graceful degradation, access permissions. I challenge you to read the texts from SEI around quality attributes, and you will find these tactics are in there. So far, everything I've introduced, what I will tell you is there is essentially a tactic to achieve each of these. And at the bottom is verification of the software architecture design. This morning we learned a little bit about validation and verification through on-the-road testing and the hologram software and the like. And then just the speech before me was talking about some of the verifications. The idea is that you need to verify the design as well. It could be as simple as design walkthroughs, although those aren't always simple, to some analysis of your scheduling, control flow analyses, things that we are probably doing, but they must be documented and proven to work for the functionality that's in question here. Okay, so from a software architectural safety, what are we talking about here? There are really two topologies that I've chosen for this presentation. I'm sure there are more than that. One view of safety from our standpoint as architects could be that safety is bidirectionally dependent on other attributes of the architecture, such as availability or security or performance. And that certainly is one way to view it. That, for example, you can't achieve safety if the software is not available, or if the software is not secure. And I would say that is a true statement. Secondarily, one of the texts that we probably all know well from SEI states that safety is its own quality attribute with tactics that can overlap some of the other quality attributes like availability. And what I'm claiming to you today is that regardless of the topology or your view, the point is that the tactics that we can use to achieve software architectural safety are the same. Okay, so what are those tactics? This is a list of the tactics that if you went through the prior slides on the presentation and picked out a lot of those methods and a lot of the goals and a lot of the mechanisms, you can start to map those goals and methods and mechanisms to tactics that we know well. And I've listed them here. Currently, you can attribute those to certain quality attributes like availability, modifiability, performance, and security. But the real takeaway is that regardless of the standard that you're reading, our goal as software architects should be to determine whether we have the tools or not already to achieve what we're being asked to do. Is this a new way of packaging information that we already know, or is this new information that we need to research? That's the real question we need to ask ourselves as architects. Okay, so for this talk regarding automotive, really there's two conclusions that we can make. Number one, functional safety expands the notion of safety that we already know as software architects, but it applies it at a system level. So a couple of things that I can point out here. One is, if you look through a lot of the discussion points around safety, software is a portion of that, and there's no doubt about that. But software is not the only portion. If the functionality that we're dealing with has electrical components, mechanical components, chemical, that all needs to be analyzed. And safety may be software may be a huge portion of that or a minor portion of that. And it depends on the industry. In today's world, you can imagine in automotive, software is a large portion of safety. We have a large role to play there. But functional safety is a system specification with sub-specifications for each of these disciplines, let's say. Okay, the second conclusion we can make is that we have a very diverse toolbox as architects. And one of those tools we have is the idea of quality attributes and tactics and the various analysis methods that you're going to hear about this week. And what I'm claiming right now is that it is my opinion that these tactics that we know and are going to learn about this week in many of the good speeches are sufficient right now to satisfy most of the functional safety that you'll see. And so our challenge is to determine where are the gaps in what we know today versus what is published out there. And so really what I want to leave you with is just one statement. This morning you learned about autonomy. And I didn't talk about autonomous here. That's as Phil mentioned, there are other standards and regulatory questions around that. But autonomy aside, you come from various industries. And the question is, do you have functional safety standards? And if you do we have the tools today to achieve those? So from an automotive standpoint, autonomy aside, we do. But I don't want to make that claim for everyone. And it's a good research topic, I would say, for all of you, is to investigate that very thing. And if there is no functional safety standard in your industry, then that's another follow-up research to think about is, okay, are there actually safety concerns with what we're doing? And then go out and look at some of these other standards and try to determine, can we apply these in our field? And that's it. Thank you.